Welcome everyone. This is the monthly Golden Gate Computer Society general meeting where we normally have a guest speaker, and we have one today. So we like to make sure everybody stays with their microphones muted. If you by any chance make noise in the background, you will become the front and center person on there. Uh, yeah, so please make sure your microphone is muted. And if you do need to ask a question, please use the raise hand button. If you look at the bottom of your screen on most computers, there should be a little react icon. It's like a little heart. And when you click on that, there's an option to raise your hand. The advantage of doing that is that you will be posted up on the top of the screen, and we'll see that your hand has been raised. And then we'll get to you either during the while the presentation is going on, or at some point where it makes sense to answer the question. You can also post a question on the chat. All right, so we have a guest speaker, which our very active member Karen has found, and I will turn it over to her to give us the lowdown and introduce him. Okay, thank you. Take it over, Karen.
Good evening, everybody. Thanks for coming to our GGCS general meeting. Our guest this evening is Adam Compton. I know him from our karate dojo in Nevada. So this is our second speaker that comes from karate origins. Believe it or not, the person that recommended he speak at our meeting was our head instructor and owner of the Ultimate Self-Defense Studios in Nevada. Jordan Penman, and he said that Adam was quite knowledgeable in many areas of IT. And I'm looking forward to seeing what he has to say about AI and self-driving cars, and that's going to be our subject for this evening. So let me welcome Adam. Thanks for coming, and enlighten us, please.
Certainly. Hi, I'm Adam. So I have do you want me to start presenting, or should I chat first about my background?
Chat first.
Yeah, go ahead and give us a little background. Thank you.
Sure. So I've been a software and infrastructure engineer for about 20 years, 20 and change. I've worked in a lot of different industries. I've worked in high finance, in advertising, in manufacturing, in enterprise. My specialty is in getting the really large scale computers that back like giant websites. So for example, I worked at a company called Slack, which does business communication software. And I was on the team that was responsible for keeping all of the servers running, the thousands of servers that accepted incoming connections. So everything in the company, all incoming communications, all outgoing traffic routed through this cluster of servers. And I was on the team that was responsible for keeping them alive and scaling them, handling security patches and incidents and outages. We were, if anything went wrong with that, it was literally instantly front page news. Like that happened several times while I was there. Things going wrong would be front page news in the Wall Street Journal the next day. So it's high pressure, but it's fun. So that's the kind of stuff I work on, is infrastructure and the pipes that keep everything running. So I can go into more detail, or I can start the presentation. Whatever you guys want.
You have the floor. You
okay.
Take over. Yeah.
Let me share my presentation then. Okay. There we go. Okay, so I have a presentation on AI and self-driving cars. The company I work at now is a self-driving car startup called Wayve, with a Y. They're based out of the UK. And I don't work on the self-driving part. I work on the have lots of computers part, but I know enough about it that I can speak like just with public knowledge about the sorts of things that self-driving cars use. So the outline for this talk, I'm going to go over some background knowledge and terminology that'll be helpful, a little bit about the history of autonomous vehicles and autonomous robots, the stack of what is actually happening inside the self-driving car, some strategies that are in common use for how to accomplish the tasks of that stack, some of the economics of self-driving cars, who the main players are, and a Q&A. I do want to emphasize that this is, I might get things wrong. I'm giving you the best of my understanding, but if there's anything that I make a mistake on, I apologize in advance. So I got in a little bit into my background, so I don't really need to recap that here, but this is the sort of work that I do at Wayve. So when we talk about self-driving, that is a kind of a abstract term. And it's useful in the industry. The Society of Automotive Engineers has these levels of self-driving that they use, that they defined, and that everyone in the industry uses so that everyone is talking about the same thing. So an SAE level 0 is there's no automation at all. SAE level 1 is minimal assistance. That's things like cruise control, right? SAE level 2 is where it starts getting interesting. This is advanced driver assistance systems. We also call that hands-off and eyes-on. There has to be a human in the car. They have to be paying attention and awake and not looking at their phone, but they don't have to be holding the steering wheel necessarily. This is things like adaptive cruise control, where it follows the person in front, lane assistance, parallel parking assistance. There's automatic stop, right? This is a pretty common level among OEM cars that exist in the world today, like Chevys and GMs and Toyotas and stuff. A lot of them have this level of automated driver assistance where they can do some things with the car, but you still have to be paying attention and driving it. Level 3 is hands off and eyes off. You still have to have a human in the car, have to have a driver, but they don't have to be paying attention. And this is the sort of thing where if the car runs into a situation it can't handle, it can stop itself. It can pull over to the side of the road and sound an alarm at the driver or wait for assistance. But it still needs to be crewed. Like there has to be someone piloting it. SAE level 4 is driverless with limited scope. So this means in a certain area or under certain conditions, there's constraints around how well it can work, but it can function without a driver. If you've been in San Francisco in the last year or so, you've probably seen the Waymo cars driving themselves around with the big spinning LiDAR on the top. Those are SAE level 4. And SAE level 5 is driverless with unlimited scope. Can drive anywhere with no preparation, with no mapping, without like off-road, anywhere that the car could plausibly go. There are no SAE level 5 technologies currently in use anywhere that I'm aware of or in active development, but that's kind of the goal. That's where everyone would like to get to. So the history of autonomous vehicles is actually a lot longer than probably people think it is. The first autonomous robot was called Shaky. It was developed at the Stanford Research Institute in 1966. And it was very simple, very straightforward. It was a big, tall robot that had wheels and had some limited computer vision, and they could program it, and they programmed it in Lisp. And they could give it instructions to say, like, you are on a table, there's an object on the table, knock the object off the table. And so the robot would develop a plan and figure out like how to get itself over to the object and then activate its little like pusher thing to push the object off. But they were able to give the robot concepts to follow rather than like turn the wheel 15 degrees and then accelerate and then turn the wheel back. So that was in the 60s. And the industry has been working ever since to make improvements there. The modern era of autonomous vehicles kicked off in 2004 with the DARPA Grand Challenge. This was a competition funded by DARPA. I want to say it was $1 million, I think was the prize, to develop a vehicle that could follow a given prearranged off-road route. And it was meant to spur the development of vehicles that could, I mean, it's DARPA, right? The Defense Advanced Research Projects Agency. To spur the development of vehicles that could operate in like war zones. So the Grand Challenge in 2004 paralleled Interstate 15 between Barstow and the California-Nevada border. Nobody won. The course was 150 miles, and the car that did the best made it about 7. So that's to give you an idea of how far we are now from where we were in 2004. That was the what they were able to do. The first urban grand challenge was 3 years later in 2007. They built, I want to say out near Vacaville. They had a fake town basically, that they built the roads and the buildings, and they had other traffic and traffic lights and signs. And the task was to travel a prearranged route of about 60 miles in length, but obey all traffic regulations, wait for lights, wait for other cars, merge into traffic, do all of the things that a car would have to do. And the winner took about 4 hours to drive that 60 miles because they, were just at the beginning of being able to do this. So the autonomy stack, this is the self-driving bit. This is what the car is actually doing to drive itself when no one is watching it. There are 4 main pieces, and sometimes people bundle the third and the fourth one. Perception is understanding the world in which the car is currently situated. Location and mapping is understanding where in the world the car is. Planning is figuring out what the car should do next, essentially. And then execution is the actual realization of the plan. Well, I'll get into that. So this is an image I found, I didn't make this, of the different kinds of sensors that autonomous vehicles can use. The long-range radar, the LiDAR, the cameras, and there's also ultrasonic sensors. This also doesn't have GPS, but that is a sensor that cars can use as well. There are other sensors that are in even less common use. There's infrared sensors. There's all sorts. I mean, anything you can think of, people try. But the basic idea of the sensor package is getting information about the world into the car's computer so that it can form the best possible understanding of the area that it's situated in, and thus avoid doing anything dangerous, and also be able to successfully navigate, the lane changes and stoplights and all that. So in terms of the sensors, I mentioned cameras. This does include infrared cameras. It's actually one of the night driving technologies that people are developing, is having infrared floodlights and then have infrared cameras. So the cars can see around them without being giant and bright and very distracting to every area they drive through. Radar is used just to tell, like, range finding and do object presence. LiDAR is radar with lasers instead of radio waves. It's much more precise, and you can actually do object identification with LiDAR, but you can't. It's very sensitive. Like it's sensitive to conditions of the LiDAR sensors themselves. So they have to be aligned and calibrated, and if they get bumped, then they have to get recalibrated. And they're also very expensive compared to the other technologies. And then I mentioned GPS, just so the car knows where it is. So the perception part of the automotive stack is broken down into these stages. Segmentation is breaking an image into pieces. Detection is identifying the objects in an image, and classification is categorizing those objects. So you might say, if you have you're just sitting in your car, you're looking out the front, out of the windshield, you see the world around you, right? You can take that as an image. You can analyze that image algorithmically. You can say, what are the areas in the scene? I see some lane lines. I see a bounding box that might represent a person. I see a stop sign. I see another car. I see a crosswalk. So segmentation is finding the different edges of an image that represent different things that are, like, physically in the world. Detection is identifying those objects. So the segmentation stage might say, this is, I'm going to draw a rectangle around this piece. This piece is distinct from the rest of the image. It is its own object, but I don't know what it is. And detection is a different pass that says, oh, that object is another car, or that object is a cat, or that object is a person on a bicycle, or whatever. Actually, I should say, I got ahead of myself. So the segmentation is breaking into pieces. Detection is identifying the unique objects in those segments. And then classification is, this is a car, this is a cat, this is a bicycle. The autonomous vehicles have to do this constantly. They're always looking at the current scene, looking at the world around them, doing this perception breakdown and going through all these modules so that they constantly have an idea of everything that's around them and can figure out what those things are and which of the things it should care about and in which ways. So the next phase of the automotive stack is the location mapping. You have to know where you are, because the point of this is to get the cars to somewhere, right? You don't, the reason to have an autonomous vehicle isn't for it to sit in the garage. So you have to know where you are so you can figure out how to get where you want to go. And usually this is done with GPS, but there are other ways of doing this because GPS is not infallible. There are areas that are not GPS mapped. There are areas inside buildings or parking garages. There are, cloudy days where GPS doesn't work. So there's also like high definition scans of locations. There's heuristics you can use. You can try and like read street signs and pull out, do text recognition on the street signs. And then the next step is planning. Given the world around you and where you are, how do you get where you want to go? This uses algorithms and heuristics to integrate the perceptions and the location to develop a plan, and then translates that plan into the control signals that actually tell the car what to do. This is the stage where the car takes into account both what it wants to accomplish. So let's say it's going to turn right soon. It needs to turn on the turn signal. Let's say it sees another car stopping, it needs to stop. It sees a bicycle crossing its path, it needs to slow down. It sees, a bus pulling over, it needs to pull around the bus, whatever. The planning stage is where it figures out what to do about the perception information that it's gotten, given where it wants to go. And then the execution stage is the basics of, I'm turning the steering wheel, 0.01 degrees, I'm accelerating and braking. And if you're level 0 through 3, where there is actually a human driver, you can notify the driver, right? You can sound a big alarm or stop the car or, flash a bright light, whatever. If you need to do something with the human. So the autonomy strategies are the ways you accomplish the things I just talked about. There's two main strategies that are currently in use today, a modular and an end-to-end. I'll get into what each of these are. So the modular strategy is the one that's most commonly in use today. It's a pipeline of discrete software components with specific jobs. So in the perception stack, you might have this part looks for other cars. This other separate part looks for lane lines. This other separate part looks for stop signs. And each of those parts takes the perception information, the cameras, the radar, the LiDAR, all that signal, and then does its own analysis on that. So to identify the different pieces of the scene that the car is in. Each of these components is designed and built by a human. So it may be the case that the classifier for, let's say, other cars uses a machine learning neural net that is trained to recognize other cars and images, but some human had to say, aha, we should look for other cars. And so they added that component, the component that does that kind of detection. So you might have dozens or hundreds of components that consider the different things a car might run into or the ways in which they might interact. So the modular stack of components is incredibly complex to reason about. It is technically a state machine in that every state is defined and transitions are defined, but it is just hellishly complex about what inputs exist and what the car is going to do and how to reason about what the car is going to do. It is all, like I said, it's all stateful. You can figure it out, but it's very complicated to work out for a person to work through. And it's also got limited flexibility, especially with compound scenarios. So let's say the car is in a situation where there is another car that's stopping right in front of it, so it's got to slam on its brakes, but there's also a car that's coming up behind it, and if it slams on its brakes, then that car might rear end it. And then also there's a kid chasing a ball across the road. Like, it's very possible to imagine that scenario happening, and the modular strategy has to essentially have either a rule or a series of heuristics that would work together to form a outcome for that, that someone has to think of ahead of time. And there's very smart people working on this. So people have thought of any situation you can imagine, but someone has to think about it. And then the last part of the modular strategy is there's redundant computation, because each of the components takes in the sensor array, takes in the perception, and does its own analysis on the scene. The other strategy that's in, I don't want to say common use, but that is in use, is called end-to-end. This strategy, you feed all of the sensor data directly into a trained neural network, and that neural network generates the control signals directly. So instead of having a module for stop signs and a module for lane lines and a module for bikes and a module for other cars, the neural network just looks at the entirety of the scene and says, oh, okay, based on the entirety of the scene, the thing we ought to do is slow down. The thing we ought to do is turn on the turn signal and turn right a little bit. This is less computational workload and can be run with less powerful hardware, because it only has to analyze the scene once. But it's incredibly challenging for what's called verification and validation, which is a term of art in the automotive industry. You have to be able to know what the driver system is doing and why. And with most neural networks, you don't know. Like, all of the information's encoded in the weights in the neural network, and there's no real introspection to know why it's making those choices. And then also, subtle changes in the input can have disproportionately large impacts on the output. Maybe someone wearing a red shirt works in a certain way, but someone wearing a blue shirt, it responds totally differently, and you don't really know why. So that's, I should say, among the reasons why end-to-end is less common is because of all these challenges of the verification and validation, but it has benefits too. So I want to get a little bit into the economics. This is not my strong suit, but I found something that I think is interesting. Many people think that the expensive part of self-driving cars is the compute, is having to have fancy GPUs. That's not actually true. Nvidia Orin is the tech platform that Waymo's cars use. And at least as of a couple of years ago, I found some articles about it, and it's only like $400. So the computer doesn't need to be very powerful, because it's mostly executing a state machine. It's not doing a lot of complicated processing anew. You construct a pipeline that's given some input and knows what to do in a split second based on that input, whether it's a bunch of different modules or an end-to-end like single neural network. The point is that the processing being done on the car is very limited, because it needs to happen quickly, because the car has to be able to react very quickly. By contrast, the sensor array, it can actually be very expensive. Most cars have cameras. They're not very expensive nowadays. Most cars have radar, especially cars that have adaptive cruise control or collision detection. The radar is pretty common and pretty cheap. But the LiDAR sensors that Waymo's use are, I found a blog post that analyzed a car and figured it probably costs about $40,000 per car. So that's almost as much as the car, if not more in some cases. So obviously not economical for everybody to have that level of sensor package. But because Waymo is operating these robo-taxis that have no humans in them and are meant to be safe and effective under all these circumstances, it's worth it for them to have that level of sensing accuracy. So the major players, the business models in the space, there's the ride hailing, which is essentially automated Uber, right? You push a button on your phone and the car appears. There's no human driver. It takes you wherever you want to go. There's a lot of players that want to do that because the unit economics are really good if you can maintain high utility. So Waymo is a subsidiary of Google. Cruise was bought by GM. Zoox is a subsidiary of Amazon, and Baidu is they operate in China. They're not like part of the Chinese government, but that company is operating and doing in China essentially what like Waymo does here. Another business model is the owner-operated model, which is um, you have the car, you own it, lives in your driveway, and it's just easier for you to drive. Or maybe it gets to the point where you don't have to pay attention while you're driving it. You can play on your phone or take a nap. Tesla's full self-driving does this. And most automobile OEMs, like I mentioned before, have some amount of this advanced driver assistance technology in it, and that they want to even improve. There's also long haul trucking is an interesting application for autonomous vehicles, because the routes are very well defined, easy to map, easy to understand. The conditions under which the cars will be driving are highly predictable. And it can be very dangerous for humans, right? Like, we push truckers so that they drive, 12 hours at a stretch and they can fall asleep. And so there's long haul trucking is very different than ride hailing, but it is useful to be done completely autonomously for different reasons. And there's companies that are in that market. And then there's also the kind of selling the picks and shovels to the gold rush kind of thing. The Nvidia is selling both the GPUs that are used to train machine learning models, and they have, I mentioned, the in-car components that are used to do the computing on and control the output. And there's a company called Mobileye, which does camera-based driver assistance for OEMs. They license their technology to OEMs, car manufacturers, that then say, like, oh, I don't know of any of Mobileye's customers, but I'm a car manufacturer, and instead of developing my own camera-based self-driving stuff, I just buy it from these guys. So that's actually, I don't have a Q&A slide. So that's the end of my presentation. I am happy to take questions that people might have about anything that I've gone over.
Well, Adam, thank you very much. That was very informative. I think what we'll do is we've got about 7:36 right now is the time. I think I'll go ahead and turn off the recording, and we'll just make that the end of our scheduled presentation. We'll open it up for question and answer. So give me a second here. I will stop the presentation. Again, thank you very much. That was very nice. And thanks everybody for being here. Don't forget to go to our website. I should have this uploaded soon. And you can, I've been putting a link on there for the meeting. So go to the meeting and go to the YouTube channel, and you'll be able to rewatch this, and make sure you subscribe and give it a like. I will stop the recording here momentarily.